So now that we know how to find area between two curves, we're going to start talking about what if we took that area between the two curves and we rotated around some axis. So we're going to start by, we're going to look at a couple different methods, but we're going to start by looking at what we call the disk method. So there's some vocab up here, so if you want to pause it and get it written down if you didn't print out the note sheet. A solid of revolution is just what's going to, basically what's going to be a three-dimensional figure that results after you rotate something around a line. Your axis of revolution will be the line that we rotated around. The disk is the shape that is formed by taking a rectangle and rotating it around an axis. So if you can see this picture here, and I know sometimes it's hard to read the writing on it, so if you look at the picture of online, if you don't print the notes out, if you even just look at it online, if it is coming out blurry. But again, notice if I take this rectangle, okay, and I rotate it around my axis, what it's going to form is what we call a disk. The disk is really in the shape, in this particular case, where it's a rectangle, it's the shape of a cylinder. So if we talk about how do I find the volume of a cylinder, and don't even worry about this picture for a moment, I find the volume of a cylinder by taking the area of the base times the height of the cylinder. If you think about a cylinder, the base is always going to be a circle, so the area of the base will be pi r squared times h. Okay. So if I look at this cylinder, notice in this particular cylinder that, so it's on its side, it's a cylinder laying on its side, that the base of the cylinder here is going to have a radius, so from the center out, of f of x. So from the center out is going to be determined, the height of the radius is determined by our function f of x. So pi times our function squared. Our height of our cylinder here is going to be our change in our x, which we often refer to as dx. So what if I wanted to find the volume of this entire curve rotated around the axis as opposed to just the rectangle? Well, then I might have something kind of more like this. And the pictures don't exactly match. I tried to find some pictures online. So they're a little bit different. As you can see, this curve is not the same as this curve, but the concept is the same. Well, notice that that would be a whole bunch of those little discs or those little cylinders. Well, what would we have then? Well, I could write that, if you think about what we learned before, I could write that in summation notation and say that the entire volume would be the sum of starting at some, so say starting at some number all the way up to some other number, pi times f of whatever x, so often called x of I, so just plugging in various x values, squared, since that's my radius, dx. So where am I getting this from? The pi radius squared, remember radius is my function, and the height, my height is dx. Well, what if I said I'm going to put in disk after disk after disk after disk, and so the more accurate I am, or the more disks I have, the more accurate I become. So I'm going to use this summation notation, and I'm going to take the limit as n approaches infinity, because the more rectangles I have, or in this case the more disks I have, the more accurate I am. Well, what is that going to do for me? Well, by definition, I can turn that into an integral. So this, I believe, was already written on the note sheet, so I can take the integral from a to b, some beginning interval to some ending interval, of pi r squared h, which, as we said, was pi times our function, because our function is our radius, and it should be squared, and I noticed it after I put the notes out, and I didn't want to redo them, dx. So let's actually look at how we're going to use that to solve some problems. Okay. So based on that, then this is the formulas that you're going to see in your book. So if we are rotating around a horizontal axis of revolution, for example, something like the x-axis, okay, so we're rotating it around here. If I took this solid and rotated around there, how do I find the volume? Well, remember I can pull constants out of integrals, so I can pull the pi out. R of x just stands for my radius, which, as we all just looked at, my radius is the same as my function. So my function gets plugged in for Rx, my function f of x. Okay. If instead I'm going around a vertical axis, so say for example the y-axis, then kind of that same idea as we looked at before. What if we're looking at the area between two curves and we're making horizontal rectangles as opposed to vertical rectangles? Because here when I rotate, let me change colors, here when I rotate around the x-axis, I'm rotating this rectangle here around. If I'm rotating around the y-axis, I'm rotating this horizontal rectangle around. So for that reason, I'm going to make sure that I use my limits in terms of y values as opposed to my limits being in terms of x values. And I want to make sure that my width is represented by dy and that my radius is represented by my function, but my function needs to be in terms of f of y instead of f of x. So in other words, solve for x as opposed to solve for y. So now that I have that long introduction for you guys, now let's actually look at doing an example. Let's say I want to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals that square root of sine x, g of x equals 0, x equals 0, and x equals pi are on the x-axis. So if I look here, I'm going to go ahead and I'm going to try to draw this a little bit. Notice I say try because my artistic skills aren't that great. So I go from 0 to pi, it looks like. So x equals 0 is here. X equals pi is here. And I have the function g of x equals 0. Well, g of x equals 0, remember that means the same thing as y equals 0. So that is going to be this axis here. And then I have the square root of sine x, which is going to look something like this. So notice that the very first thing I'm going to do is I'm going to come up with the function that represents the area in between my two curves so that I can rotate that around and find that volume. Well, notice that the area in between the two curves is top curve minus bottom curve. So I'm going to take square root of sine x minus 0, and I still have the square root of sine x. So when this gets rotated around, it's going to look something like, so it's going to end up being, think of this as a three-dimensional figure, which does not look three-dimensional at all. But it's going to be that kind of three-dimensional figure as it gets rotated around. So then according to my formula, I rotated around a horizontal axis, about the x-axis to be specific. So my volume is going to be equal to my two limits from 0 to pi of my area, which I found was top curve minus bottom curve. I don't really need to write the minus 0. dx, and I need to put, and I apologize, I need to have a pi in front, and I need to square my function. So now I have the accurate integral set up. From here, I'm going to go ahead and just punch that into my calculator. As I said before, I feel like we've practiced integrating enough, and I'm going to go ahead, and my calculator tells me it's about 6.283. I always remember to go to 3 decimals. And then I never had any units, so I'm not going to worry about units, but there is my volume. So looking at, I believe there are 3 examples total. So this may be a little bit longer video, I'm sorry, but I would stick with all 3 because they are all 3 slightly different. So doing the same idea, I want to find the volume formed by revolving the function 2 minus x squared and g of x equals 1 about the line y equals 1. So I'm going to go ahead and draw this. I have my function 2 minus x squared, so I could put this into my graphing calculator because it is in terms of y equals. But I do know it's a parabola, it's upside down, and it's shifted up too. And I also have the line g of x equals 1, so I'll use a couple different colors. So g of x equals 1, or y equals 1, and 2 minus x squared. So I'm going to look something like that. So I'm taking this area here, and I'm rotating it around that line y equals 1. So when I do, I'm going to have something like, and it rotates around. So again, that three-dimensional figure. I'm terrible at drawing three-dimensional figures. I'm really sorry. But it's going to look something like that. So what I want to do is I want to say, okay, so I need to first figure out where is it intersecting here, because I need my upper and my lower limit. So remember, I find intersecting by setting my two functions equal to each other. 2 minus x squared. So in the previous example, I was told my limits equals 1. So I rearrange this because it's quadratic, and I end up with 0 equals x squared minus 1. I go ahead and solve this, and I get x equals plus or minus 1. So I'm going to have the integral from -1 unto 1. My radius is going to be this rectangle here. Well, how do I find out the length of that rectangle? Well, notice it's just going to be my top function minus my bottom function, top curve minus bottom curve. Okay, so I will have, for my radius, I have to have my pi out here. I always want to forget that. My radius is going to be 2 minus x squared minus 1 squared dx, which is the same thing as saying pi times the integral of negative 1 to 1. I always simplify these because it means I have to punch less into my calculator. Of 1 minus x squared dx. That will give me the volume of this awesome three-dimensional figure I drew. And it's about, I punched into my calculator, about 3.352 for my answer. And then moving on to the last example. So what about this one? I have a table leg that has a circular cross-section. It gives me the radius, this crazy function. The height is 100 centimeters above the ground. I have to find the volume if I rotate around the y-axis. So notice now the other one, this one and the previous one, I rotated around a horizontal line. So now I'm going to rotate around a vertical line. So let me draw my table leg. So it has a radius that is 3 plus cosine pi y over 25. I don't know what my table leg looks like, maybe something like this. It's a really fancy table leg. I probably should move it up because it tells me that it's 100 centimeters. So there's my table leg. Pretty fancy. So then I also know that this total height is 100 centimeters. So the thing I want you to be careful of is that's not telling me the height of my cross section or height of one of my discs. That's telling me I'm going from 0 up to 100 on the y-axis. So that's telling me when I set my integral up, I'm going to have pi times the integral of 0 to 100. My radius is 3 plus cosine pi y over 25. So I'm going to plug that in and square it. And then my width, or is my dy, so that's kind of where the width comes from. It's the other piece of my function. From here, again, I have had a lot of practice with integrating, so rather than have to integrate this by hand, I'm just going to put it into my calculator. And when I do, I get about 942.478. And because it told me the units, I'm going to go ahead and say centimeters cubed because it's volume. And that will be the volume of my table leg.